I am Vaibhav from Vaibhav E-Learning Academy. Today we are going to continue our topic in chemistry, that is atomic structure. In today's video we will be discussing about atomic spectrum, and this is our part number 3. In today's video these are the topics which we will be covering. First one, what is a spectrum? We will discuss what is the spectrum. We will see the definition of spectrum. Second is types of atomic spectrum. Then atomic spectrums are of different types. We will be looking at what are the different types of atomic spectrum, and in this video we will be particularly talking about one type of atomic spectrum. Then we have the Rydberg's formula. Now Rydberg gave a formula and we will be discussing about what was that formula and how to derive that. Then we learn about some series, atomic spectra series. So there are four to five main series for atomic spectra which we will be discussing later on in this video. So now let us start the video with the first topic, that what is spectra. So first we will be learning what is the definition of spectra. So spectra is something that we know from the starting, that when white light is passed through a prism, it dissociates into some lights. So we will see that. Spectrum. Now what is a spectrum? The scattering of white light into different wavelengths. Scattering of white light into different wavelengths is called spectrum. This is the basic definition. The scattering of white light into different wavelengths is called spectrum. Now, different wavelengths. We can also say one more thing, that this is the simple basic definition. The correct definition, full definition is when white light is passed through a prism, it emits radiation of different wavelengths. When white light is passed through a prism, it emits radiations of different wavelengths. This is called dispersion. So when you are passing a white light through a prism, it dissociates or it emits radiation of different wavelengths. Emits, or in the sense we can say splits, or it splits into radiation of different wavelengths. This is called dispersion. The pattern of the radiations after dispersion is called spectra. So when white light is passed through a prism, it splits into radiation of different wavelengths. This is called dispersion. The pattern of the radiations after dispersion is called spectra, or basically you can say the scattering of white light into different wavelengths is called spectrum. Now this different wavelengths, what does this mean? Let me explain. So we all know that you take a prism, you pass a white light through it, it dissociates into 7 different colors, that is violet, indigo, blue, green, yellow, orange and red, the Vibgyor. So this thing is called as spectrum. Now there are some types of spectrum. Now we all know one more thing about white light, that the visible light, the white light comes in the radiation of, from 4000 to 8000 angstrom. So this is, we learned about this in the reflection video, that the visibility of the white light is from 4000 to 8000 angstrom. That is the wavelength of the visible light. This is the only frequency of light, wavelength of light which a human eye can see. So this was all about spectrum. Now we are to the second part of the video, that is what are the types of spectrum. So basically we have two types of spectrum. One is emission spectrum and one is absorption spectrum. There are two classifications of spectrum. One classification is depending upon what is the material, what is the emitting, what is the source of the light, and the second classification is about how is that depicted on the photographic plate. So atomic spectra first we can say is emission, and one is absorption. This is one basis of classification. There is one more basis of classification, that whether it is continuous, discrete or band. Now some books say that continuous, discrete and band are a part of emission spectrum. Some say that these three are part of both, but actually it is a different method of classifying it. So emission and absorption, how are they classified? This is classification based on source, and this classification is based on result. So you can combine anything. You can say emission continuous spectrum, you can say emission discrete spectrum, emission band spectrum, or you can say absorption continuous spectrum, absorption discrete spectrum. Discrete is also called as line spectrum, or it is also called as discontinuous spectrum. Or discontinuous spectrum and band spectrum. In today's video, our main goal is about emission spectrum, and we'll be discussing about emission continuous and emission discrete. I'll also give a brief intro on what is absorption, what is band, but still our main topic is from emission spectrum, this much. So these were the types of spectrum. So first of all, what is an emission spectrum? Now emission spectrum, as I said, this classification is due to from where the source is. What is the source? So the first one is emission. What is emission spectrum? The spectrum produced when light is produced from self-illuminating or self-luminous or self-illuminating objects is passed through a prism. The spectrum produced when light is produced, the spectrum produced, or we can say here formed. The spectrum formed when light produced from self-illuminating objects is passed through a prism. Now, as I said, from the source. Now, what is the source of the light? If the source of the light is something which is self-luminous, for example, a candle, for example, sun, candle, and tube lights, these etc. These things are these self-illuminating things. That is, they produce light on their own. Here we are not heating anything. So even if we are heating the solid substance over here. So that is, if you take example of a bulb, you are heating the tungsten inside that. So you are not heating any gases, you are heating the solid, or that is a self-illuminating object. If you take a sun, it is self-illuminating object. Candle, it is self-illuminating object. So these, when the light from these sources are passed from a prism, and that prism, when it gives out the rays, see, actually if you visualize this, this is the prism, this is how the light goes in, and this is a photographic plate. So this is the plate. Now when you are producing the light on this, it can be, as I said, that if a white light is produced, it passes into, it dissociates into 7 colors, VIB, and this thing, these lights go on and hit on the photographic plates, and here the colors are produced. This is what a spectrum is. Now, emission spectrum, the spectrum formed when light is produced from a self-illuminating object. For example, here you are keeping a candle. The light from this candle is passed through a prism and it will dissociate into its colors, the number of colors, which we will be discussing later on. Now this was about emission spectrum. Now the study of spectrum or the use of spectrum is called as spectroscopy, and the device used is called spectroscope. Spectroscope is the device which you use, and the plate, the photographic plate, is called as spectrogram. So this was about emission spectrum. Now after emission spectrum we are going on to continuous spectrum. Now what is absorption spectrum? Absorption spectrum is something that when you are heating a gas, or when you are passing the gas, or when you are taking a gas and then you are providing it electric energy, or you are providing burning it with a Bunsen burner, then that it produces some radiations, it produces some light, and that light when you pass through the prism, it dissociates into some colors. That is called as absorption. But we don't need that in this video. After emission spectrum we have continuous spectrum. Continuous. Now what is a continuous spectrum? So now we are going to learn about continuous spectrum. So when light is passed through a prism, if all the 7 colors are present without any sharp boundary and they merge into each other, the spectrum obtained, or this spectrum, is called as continuous spectrum. So what does this mean? So it is like in a 9th class in Newton's laws of motion, there is an experiment that if you take a stick, you take a disc or a CD and you paint all the 7 colors of the rainbow into that disc, and when you apply that, or when you put that CD inside the rod and when you spin it fastly, that all the colors merge into one color and formed a white color. That is called as Newton's disc. So before merging into white color, if you observe that, you will find that a continuous spectrum example you can see over there, that all the colors are present, all the 7 colors are present, and none of the colors are separate. Like here it is a violet color, VIBGYOR, Vibgyor is the color scheme. So violet, as soon as violet is over, indigo is present. But in continuous spectrum, you can't differentiate where is violet ending and where is indigo starting. Similarly, in green and yellow case, you cannot say where the green is ending and where the yellow is starting. They are merged into each other. So now we know that it is from 4000 to 8000 angstrom. In continuous spectrum, even 4001 angstrom, 4002 angstrom. So even for violet, we have dark violet, we have light dark violet, then we have super light dark violet, then we have violet, then light violet, dark light violet. So because of these, there are 4000 wavelengths. So even for one color, you can take an infinite amount of, like we can take 4000.1 angstrom, 4000.2 angstrom. Each intensity of that violet is different, but that is violet color. And where violet ends, that indigo starts. So this type of spectrum is called as continuous spectrum. Now after continuous spectrum, we have one more type of spectrum, that is discrete spectrum. So discrete spectrum is also known as a line spectrum. In this, what happens is it does not merge into each other, or you can see the boundaries between them. In discrete spectrum, you cannot see all the 7 colors, only some specific colors are found, and this is the most important spectrum out of all these spectrum. Discrete or line spectrum. What is discrete or line spectrum? Same thing when you are passing light through a prism after the result. So what happens is the light passed through a prism if all the colors of Vibgyor are not visible. it is called line spectrum. So the light passed through the prism if all the if a light is passed through a prism, all the colors of the figure are not visible, then it is called as a line spectrum. So what happens is, same here, this is a prism. Now here you are passing a light, or white light, or any light you are passing. This is the plate. So what you will observe, for example, let us take one gas you took. You heated a gas, for example, hydrogen gas. If you heated it, what happened is, you see that here is one line, here is one line, and here is one line. So actually this is starting from 4000 to 8000, it is supposed to be. So if it was a continuous spectrum, you will see 4000.1 and then 4001, 2, 3, 4 up to 8000. But here what you are seeing is 4000 is present. After 4000, directly 4125 angstrom is present. The numbers between them is missing. After that, suddenly you see 6297 angstrom is there. 6000 to 4000, too much difference is there. Then here you suddenly have 7989 angstroms. So here what you say is only some are present, only some wavelengths of light are present. This type of spectrum is called a line spectrum. Why is it named as line spectrum? Because of these lines. So what happens here is, not all the colors are visible, only some specific colors are visible while others are missing. Now this property of hydrogen, this color scheme is only specific to hydrogen. This is just an example of value, this is not the correct value. So for example, this is hydrogen. So each time you heat an hydrogen, each time hydrogen gives out its rays, and when you pass that through prism or any machine as a spectroscope, if you pass through that, what you see is only these colors will be present, other color won't be present. So we can conclude one thing, that line spectrum is characteristic for each and every element. So here it is characteristic for every element. It means that, for example, hydrogen, then it will show only that system. If you take, for example, neon is also a gas. If you heat neon and if you pass that through that spectroscope or spectrum machine, whatever that is, and if you see that plate, then it will also have some specific color coding. That is called as line spectrum. So where is it helpful? For example, we give you 3 to 4 gases, or if we give you one gas and you have to identify which gas is that. We don't know, we don't have any smell, or we won't be using any flame test or everything. What we do is we just heat that, and that to electric heating. We heat that. After heating, it produces some radiation. This radiation is passed through the spectroscopy machine, and after that it produces some rays. In that photographic plate, it produces some lines are marked, and if you check that with the references, you will find out that this marking is for hydrogen, this marking is for neon. So wherever this marking is matching, that is that element. So it is called as fingerprinting of gases. So you can say like that also. So this was all about discrete or line spectrum. Now, till now we are learning that you are heating a gas, it is producing radiation. You are heating a gas, it is producing radiation. You are taking a solid substance or anything, if you are heating it, it produces radiation. And that radiation we are passing through a prism. But now, what is that radiation? What is the form of that radiation? From the previous video, we learnt about the Bohr's model of atom. In that, Bohr said that the electrons are present only in some discrete locations. So for example, this is a nucleus, shell number 1, shell number 2, shell number 3, KLM. So this is n is equals to 1, n is equals to 2, n is equals to 3. And suppose this is a hydrogen atom. So there is one electron over here. So as we said that we are heating everything, right? So let us heat this atom. If you are heating it, what is the energy level of the first orbital? From the previous video, we have learned that energy is equals to minus 13.6 into z square by n square. From the previous video, you have to watch this video if you want to understand how this formula came. So now for shell number 1, minus 13.6 for energy of first orbital, minus 13.6 into z is 1 because it is hydrogen. What is z? Z is atomic number. 1 square by 1 square. So energy of first orbital is minus 13.6. Unit is electron volt. Similarly, E2 is equals to minus 13.6 into 1 square by 4. So 136 by 40. 6 4 2 0 3 2 10 3.2. So energy of the second level is equals to minus 13.6 by 4, which is equals to minus 3.4 electron volt. Minus 3.4 electron volt. Similarly, E3 if you take, that is minus 13.6 into 1 square by 2, sorry, this time 3. So 3 square is 9. This value you will get minus 1.51 electron volt. So this is the energy level. Now you are heating this according to thermodynamics, which we'll be discussing later on sometime in other series. But according to thermodynamics, first off, that we can say that energy is in two forms. One form is work and one form is heat. Here on this microscopic hydrogen atom, we cannot perform work. So what we do is we heat it. While we are heating it, we are providing energy to it. Here it is minus 13.6. What is minus 13.6 electron volt? That is the energy. And we all know that energy is inversely proportional to stability. So more the energy, less the stability. Lesser the energy, more the stability. So here it is minus 13.6 electron volt. And here 3.4, 1.5, which is least, which energy is the least energy? That is minus 13.6. Because it is the largest value in negative. So it has the least energy. Least energy means more stable. So what you are doing is you are providing heat. After providing heat, this electron jumps from shell number 1 to shell number 2. This jumping is called excitation. What is excitation? You are providing some heat, some energy. You are providing some energy to this electron to jump from shell number 1 to shell number 2. But here you are providing heat, it is coming to its second shell, it's okay. But the electron does not want to remain in its second shell. Why? Because every particle in this universe wants to remain in its lowest stability, lowest energy state. So if it is the lowest energy state, the stability is higher. Each particle in this universe wants to be more stable and has less energy. So what it does, after reaching to shell number 2, it tries to go back to shell number 1. This is called de-excitation. De-excitation. Now, when it is de-exciting, the thing is, if you want to enter this shell, the necessity is that it should have minus 13.6 electron volt. So, when it is going from shell number 2 to shell number 1, it emits some radiations. This, you can say radiation, or you can say this as photon. We'll learn photon term, we'll learn in Max Planck's quantum theory, that will be in the next video. But this, it emits some radiation. It has to lose some energy to go to N is equals to 1. How much energy does it lose? So delta E is equals to E2 minus E1. So where it was in the starting? In the starting it was in N is equals to 2, that is minus 3.4. Minus E is equals to 1 is minus 13.6. So minus 3.4 plus 13.6, that is equals to 10.2 electron volt. So what does this 10.2 electron volt mean? It means that when the electron is revolving in its first shell, in its original state, in its rest state, what you are doing is you are providing 10.2 electron volt of energy. You are giving it to the electron. After getting that energy, it jumps to the second orbital, n is equals to 2. Here this jumping is called excitation. It is jumping to its second shell, but it does not want to remain in second shell because it wants to become more stable, and at shell number 2 it is not stable. So it wants to go back to its original state, or it wants to go back to its ground state. So what it does, it jumps back to shell number 1, and when it is jumping back, the amount of energy which we provided to the electron, it gives that much energy back to us. So that giving of energy is how much? 10.2 electron volt. So while going from n is equals to 2 to n is equals to 1, while jumping back to its original place, what it does, it gives us 10.2 electron volt of energy in the form of radiation. That radiation is what we are passing through the spectroscopy machine, then that is showing us the spectrum. So here this thing is called a photon, or you can say radiation. Now if this is a radiation, we know the energy of radiation, but this radiation coming out, how can we say what is the wavelength of this radiation? Because when we took the hydrogen example, when we heated it, it gave us some characteristic wavelengths. It gave some characteristic, like for example it was what, 6700 something angstrom it gave. How do we calculate that? For that we have another formula. So this concept, did you understand? What we did was, electron was its original state, it was revolving, we provided some energy to it. After providing some energy, this electron jumped from its ground state to the shell number 1. It can also jump to shell number 2 if you provide more energy. After jumping to shell number 1, how much energy did we provide? We provided 10.2 electron volt of energy. If you provide 10.2 electron volt of energy in the form of heat, because we are heating it, so the electron is jumping from n is equals to 1 to n is equals to 2. In n is equals to 2, it is unstable, but it wants to remain stable. So what it does, it's jump back. So let me write the steps actually over here. First step is, we provide energy in the form of heat. And how much? 10.2 electron volt. Here we are taking a case that it is jumping from n is equals to 1 to n is equals to 2. Second state, the electron jumps to n is equals to 2. Third state, it wants to attain stability. Fourth step, it jumps back to n is equals to 1 and releases energy. How much? 10.2 electron volt. So the electron is revolving. What we are doing is, we are providing it energy in the form of heat. Then it is excited and it is coming to n is equals to 2. After n is equals to 2, it does not want to remain in that place because it wants to attain stability. But to attain stability, it has to go to n is equals to 1, and to reach n is equals to 1, its energy should be minus 13.6. So the extra energy it has, it emits it outside, this thing, in the form of radiations. Now when it wants to go back to n is equals to 1 for its ground state, it emits the energy in the form of radiation. That radiation, we are capturing it, we are producing it into the spectroscope, and it produces the atomic spectra. Now how much energy does it give out? That is delta E is equals to E2 minus E1, that is 10.2 electron volt. Now this energy we found, what is the energy of this radiation, we got it, but we have to find what is the wavelength of that radiation. To find the wavelength of that radiation, we have one new formula, and this formula helps in finding out the the wavelength of the radiation. The formula is E is equals to hc by lambda. E is equals to hc by lambda. Here what is E? Actually E is the energy released or absorbed by the radiation. Here h is the Planck's constant, and the value of Planck's constant, let me write it over here. The value of Planck's constant is 6.636 into 10 to the power minus 34 joule second radiation, and C is speed of light. The speed of light is 3 into 10 to the power 8 meter per second. And lambda is the wavelength. Wavelength of radiation. This E is equals to hc by lambda. This is one of the most important formula in this for finding the wavelength of the radiation. Now there is one more formula by which we can find the wavelength of the radiation, but we'll discuss that later on. Now we have to find the lambda. What was our case? Our case was, let me draw that image once again. So here the electron from shell number 2, it jumped to shell number 1. How much energy did it liberate? Energy liberated was 10.2 electron volt. Okay. Now we have to find the lambda. See, the electron, we excited it, then it got excited and it came from n is equals to 1 to n is equals to 2. Now it wants to go back to its original state, n is equals to 1. To go back there, it needs to release some energy. How much energy did it release? It released 10.2 electron volt of energy. Now we have to find lambda. So lambda is equals to hc by E. So 6.636 into 10 to the power of minus 34, 10 to the power 34 joule second into 3 into 10 to the power 8 divided by 10.2. This is a very long calculation. So to cut out this calculation, what we are doing is, see, this h is a constant, c is also a constant, h is Planck's constant, c is the speed of light. So constant into constant, if you multiply, you can rather use this E is equals to 12375 by lambda. This is one shortcut for this formula, because h and c are constant. If you multiply them, their value will be same. So E is equals to 12375 by lambda. So we can say that lambda is equals to 12375 divided by E. This is our lambda formula. Now instead of doing this calculation, we can directly say lambda is equals to 123,750 by 102. This is the wavelength. So the radiation which is emitted from this electron, it has the energy of 10.2 electron volt, and the wavelength of that radiation is this value. And if you substitute this formula, here energy we should substitute in the form of electron volt. Here lambda should be in angstroms. If you substitute energy in electron volt, then you will get lambda as in the form of angstrom. Now this was one formula, that is E is equals to hc by lambda. But this case is like a very specific case when they will give you the energy. But what if they did not give energy? In that case, here comes the third part of the video, that is Rydberg's equation. Now what is Rydberg's equation? So same thing, as we assumed in that hydrogen atom, that electron is jumping from n is equals to 2 to n is equals to 1. So what was delta E in that? Delta E is equals to E2 minus E1. Delta E formula, what is the delta E? Delta is the energy released or absorbed by the spectrum. By the radiation. Delta E is equals to hc by lambda. Now E2, from the Bohr's model of atom, E2 is equals to minus 13.6 Z square upon N1 square. E2 minus E1, from where to where? It should be N2 square. Because it is going from shell number 2 to shell number 1. Minus E1. E1 is minus 13.6 into Z square by N1 square. Now this minus and minus will add up to become plus. After becoming plus, you take 13.6 common. So 13.6 into Z square by N2 square, or Z square also will take common. Z square into 1 minus N2 square minus 1 minus N1 square. If you are taking plus 13.6 common, that will become minus N. So this becomes 1 by N1 square, minus 1 by n2 square. So what I did here is minus 13.6, so what here is minus 13.6 into z square by n2 square, and this minus and minus becomes plus 13.6 into z square by n1 square. Okay, now if you take plus 13.6 common, 13.6 if you are taking common and z square you are taking common, here it is minus, right? So it will become minus 1 by n2 square plus 1 by n1 square. So you are just putting the n1 over here and n2 over there. So this equation we will get. So finally, we can say that hc by lambda is equals to plus 13.6. 13.6 into z square into 1 by n1 square minus 1 by n2 square. Now what we are doing is we are bringing this hc over here. So 1 by lambda is equals to 13.6 z square by hc into 1 by n1 square minus 1 by n2 square. Over here if you are seeing 13.6 z square by hc. Now here remove the z because z can be variable. For hydrogen it can be 1, helium 2, etc. Here 13.6 by hc. 13.6 is a constant, h is a constant, c is a constant. So instead of writing this whole value every time, we will rather write r. So this thing we can write it as r. So finally this was what we did till now. Finally our equation becomes 1 by lambda is equals to r z square upon 1 by n1 whole square minus 1 by n2 whole square. This is called Rydberg's equation. This is our Rydberg's equation or Rydberg's formula. So let me again explain what we did here. Delta E is actually hc by lambda and E2 is minus 13.6 into z square by, see, E2 and E1. E2 is from where you are going and E1 is where you are reaching. From the point to where. So here in that case we took from n is equals to 2 to n is equals to 1. So instead of that we are assuming n1. So E2 is equals to n2 square plus 13.6 into z square by n1 square. So from where to where? The electron was excited. It got de-excited and it emitted the radiation. When it is de-excited, it is going from n2 to n1. n2 is shell number 2, n1 is shell number 1. From n2 to n1 it is going. So final is initial is n2 and final is n1. Here what we did, how it became plus, minus into minus is plus. Now you take 13.6 into z square as common. Plus you are taking common, minus is still remaining. So minus 1 by n2 square plus 1 by n1 square. Why? Because it is plus. So what we did was n1 we took here, n2 we took that side. So it became 1 by n1 square minus 1 by n2 square. Now hc by lambda. This hc we brought it over here. And 13.6 z square by hc. This 13.6 by hc we gave it the name as r. Here r is Rydberg's constant. And its value is approx 1.09 into 10 to the power 7. But this every time, see, here we have to do a lot of calculation. So r here is 1.09 into 10 to the power 7. But instead of remembering r, we can remember 1 by r. 1 by r is equals to 911 angstrom. So let me write it over here. 1 by r is equals to 911 angstrom. This will help us so much in in the forward of this video. So now this is the equation which we got, and this equation is called Rydberg's formula. By using this we can easily find the lambda of the radiation. See, we can use both this formula and that E is equals to hc by lambda. Here when we can use this formula, when energy is given to us. If energy is not given, if they give only from shell number this to shell number that, so that time you have to use this formula. So this was all about Rydberg's Rydberg's formula. Now let us move on to the different series of spectra. So let us see. So now we will be moving on to some different series of atomic spectra. So before moving on to that bigger table, let me do it in a simple way first. This is the n is equals to 1. N is equals to 2. So here it is n is equals to 1, n is equals to 2, n is equals to 3, 4, 5 up to infinity. Now suppose this is an hydrogen atom. What is this actually? Same thing which we had done like this. What we did is we cut a part like this. And this thing we are representing it in a horizontal manner. Same thing, nothing else. Now you have excited an electron to go from n is equals to 2 to n is equals to 1. So what it was, you excited it, from n is equals to 1 to n is equals to 2. Now that electron wants to come back to its stable state. From where will it come? From n is equals to 2 to n is equals to 1. So it will come like this. Case number 1. Second thing, for example, you have excited an electron to go from n is equals to 1 to n is equals to 3 directly. So it wants to come back to n is equals to 1. So it will come like this. Similarly, from n is equals to 4, n is equals to 5, and up to infinity, from n is equals to infinity. So if from n is equals to infinity it comes back to n is equals to 1, this series is called as Lyman series. What is Lyman series? If from n is equals to x to n is equals to 1, if electron de-excites or jumps from, if electron jumps from n is equals to x to n is equals to 1, then that series is called Lyman series. Now this first, from n is equals to 2 to n is equals to 1, this line is called first line of Lyman series. This one is called as second line. Even first line is also represented as alpha. So this is alpha. Second line is represented as beta. Third is represented as gamma. And up to infinite one is last one is represented as sigma. Or delta, not sigma, delta. So this is the last line of Lyman series, first line of Lyman series. So this is the Lyman series. Now what is the range of Lyman series? So here, for example, they give us what is the wavelength. So there is a question over here. Find lambda if an electron of hydrogen atom jumps from n is equals to 2 to n is equals to 1. So we have to find it. Now n is equals to 2 to n is equals to 1. They did not give the energy over here. So what you have to use is that formula. 1 by lambda is equals to rz square into 1 by n1 square minus 1 by n2 square. n1 is where you are reaching, n2 is from where you are going. So from here n2 is 2. So r into z is 1 because it is given as hydrogen. So 1, let it be as 1. 1 by n1 square, where is it reaching? 1. So 1 by 1 square minus 1 by, from where is it reaching? From n is equals to 2. So 1 by 2 square. So that is r into 1 minus 1 by 4. That is equals to 3r by 4. 1 by lambda is equals to 3r by 4. Lambda is equals to 4 by 3r. Now I said to remember 1 by r is equals to 911 angstrom. Okay. So lambda is equals to 4 by 3 into 1 by r. We can represent it, right? So lambda is equals to 4 by 3 into 1 by r value is 911. Now if you assume this as 912, why we are assuming 912? It is because we have to cancel it for easy cancellation. So lambda is equals to 4 into 304. So lambda will be equal to 1216 angstrom. So from jumping from n is equals to 2 to n is equals to 1, the lambda is 1216 angstrom. The wavelength, if the electron is de-exciting from n is equals to 2 to n is equals to 1, so it will emit a radiation. Energy of that radiation they did not ask, plus they did not give, plus it is 10.2 electron volt, we know that. That is the energy, but they asked us the wavelength. The wavelength is 1216 angstrom. How we found? We found it using this formula over here. Now this is the first line of Lyman series. Now similarly, if they ask us from n is equals to 3 to n is equals to 1, if they ask n is equals to 3, then instead of n2 we have to substitute here 3. Instead of 4 it will become 9. 9 1 is 9, 9 1 is 8. So instead of 3 it will become 8 by 9. Then here it will become 9 by 8r. So here also it will become 9 by 8 into 1 by r. So this will be again 9 by 8 into 912. After that, this step we have to reduce it. Lambda is equals to 9 by 8 into 912 angstrom. So 8 ones are 1, 32, 4. One 026 angstrom. So let me check it again. 912 by 8. 114. So 9 into 114, 36 balance 3, 9 is 9, 11, 12, 9. So the second line, if the electron jumps from n is equals to 3 to n is equals to 1, then also it emits some radiation. That energy released, how much will be the energy released? Delta E will be equal to E2 minus E1. E2 is what? N is equals to 3, the energy level is minus 1.51 minus of minus plus 13.6. So it will be 13.6 minus 1.51. So it will emit 12 electron volt of energy. That radiation will have 12 electron volt of energy, and the wavelength of that radiation will be 1216 angstrom. So we see that when it is jumping from second orbit to first orbit, the lambda is 1216 angstrom. But when it is from n is equals to 3 to n is equals to 1, then the lambda is 1026 angstrom. Why is this difference like this? The smallest one is having 1216 angstrom, and this larger one is having less lambda. So if you remember our equation, according to the first equation, we learned that E is equals to hc by lambda. So if the energy increases, then lambda decreases. Energy is inversely proportional to wavelength. So here, when it was jumping from n is equals to 2 to n is equals to 1, the energy which was spent was released was 10.2 electron volt. But when it jumped from n is equals to 3 to n is equals to 1, the energy was 12 electron volt. Energy was increased. When from n is equals to 3 to n is equals to 1, the radiation had more energy. As it had more energy, it will have less wavelength. So that equation, this is the relation between energy and wavelength over here. Now, this was the first line of Lyman series, second line. Let us move on to the last line of Lyman series. We have to find what is the limit of Lyman series. Last line is from infinity to 1. So let us take n is equals to infinity to n is equals to 1. So here 1 by lambda is equals to r into, let z be 1. 1 by n1 square is 1 square minus 1 by infinity square. Infinity square is infinity. 1 by infinity is equal to 0. So this whole value will be equal to 1. Because this value becomes 0, so 1 minus 0 is 1. So 1 by lambda is equals to r, lambda is equals to 1 by r, and 1 by r is 911 angstrom. So from n is equals to infinity level to n is equals to 1, this is delta. From lambda is equals, from n is equals to infinity to n is equals to 1, the wavelength is 911 angstrom. From, if you have to make an electron exit the atom, what you have to do is you have to provide the higher amount of energy. Since it is coming from infinity means out of the atom. From out of the atom you are bringing it inside. So what you are doing is you are providing, it is releasing a lot of energy. To reach n is equals to 1, infinity, let us take any value, but you have to put 13.6 electron volt. From here to here, the energy is 13.6 electron volt. This is large energy, and the energy is large, and the relation is E is inversely proportional to lambda. So because more energy, this has less wavelength. So the first line of Lyman series has 1216 angstrom, and the last line of Lyman series has 911 angstrom. So from these values, we can say that range of Lyman series is 911 angstrom to 1216 angstrom. This was all about Lyman series. Now one more point to be noted is the visible light falls from 4000 angstrom to 8000 angstrom. This is less than that. So this falls under ultraviolet, UV. These are UV rays. We cannot see them. So the Lyman series forms under UV rays. Now the limit of the Lyman series is from 911 angstrom to 1216 angstrom. What is Lyman series? If the electron jumping from any orbital, n is equals to any x number, from that when it jumps to n is equals to 1, then that series is called as Lyman series. So now let us move on to the second series, that is Balmer series. Let us see. So now we have the second series over here. For example, if you are heating an electron or exciting an electron which is going to n is equals to 3, but instead of coming back to n is equals to 1, it is coming to n is equals to 2. So from n is equals to 3 to n is equals to 2. Or from n is equals to 4, it is coming to n is equals to 2. It is not reaching the first state, it is reaching the second state. Similarly, from n is equals to 5 to n is equals to 2. From infinity to n is equals to 2. This series is called as Balmer series. What is Balmer series? From n is equals to x to n is equals to 2. This is called as Balmer series. So now similarly, now we will discuss about the same thing which we discussed in Lyman series. From n is equals to 3 to n is equals to 2. N is equals to 3 to n is equals to 2. Find lambda for hydrogen atom. So 1 by lambda is equals to r, r z square 1 by n1 square minus 1 by n2 square. So r is r, z is equals to 1, so 1 into 1 by, this time we are reaching n is equals to 2, so 2 square will be 4, minus 1 by n2 square. N2 is from n is equals to 3 to n is equals to 2, so 1 by 3 square is 9. So r into LCM is 36, 9 minus 4, r into 5 by 36 is equals to 1 by lambda. LCM is 36 into 9 minus 4, 5 by 36 square. So now 1 by lambda is equals to 36 by 5. Lambda is equals to 36 by 5 into 1 by r. Now 1 by r value is 911 angstrom. So lambda is equals to 36 by 5 into 911. For easier calculation, let us take this as 910. So 5 ones are 5. Here lambda is equals to 5 ones are 4182. 36 into 182. So 6552. So 6552 angstrom. So when it is jumping from n is equals to 3 to n is equals to 2, so the wavelength is 6552 angstrom. The electron wants to come back to n is equals to 2 from n is equals to 3. Then the energy released will be n3 minus n2, and wavelength of that radiation will be 6552 angstrom. This is called as first line of Balmer series. This one is first line of Balmer series. Now you can also try from n is equals to 4 to n is equals to 2, or n is equals to 5 to n is equals to 2. But here let us take from n is equals to infinity to n is equals to 2, because we have to find what is the limit of Balmer series. To find the limit of Balmer series, we have to make the electron de-excite from n is equals to infinity to n is equals to 2. So 1 by lambda is equals to r into 1 by 2 square, that is 4, minus 1 by lambda. This is 0, so 1 by 4. So r by 4 is equals to lambda. R into 1 by 4 is equals to, because this is 0, so 1 by 4 minus 0 is 1 by 4. R by 4 is equals to 1 by lambda. Lambda is equals to 4 by r. So lambda is equals to 4 into 1 by r. 1 by r is 4 into 911 angstrom. So 4 ones are 4, 4 ones are 4, 3644. Lambda is equals to 3644 angstrom. So when you are de-exciting the electron from n is equals to infinity to n is equals to 2, the wavelength of that is 3644 angstrom. Because same thing, we can say that energy is inversely proportional to lambda. So from n is equals to infinity, from outside of the atom to bring it to the center, n is equals to 1, you need a large amount of energy. And for that large amount of energy, because of that, you have less wavelength. So the limit of Balmer series is from 6552, 4 by r, right? So 4 into 911, 3644 angstrom to 6552 angstrom. This is the limit of the Balmer series, and this series forms under the visible light. So we can see this series. So now this was about the Balmer series. So Balmer series is from any orbital, if it jumps to n is equals to 2, then that series is called as Balmer series. So similarly like this, we have 2 or 3 more series, but we won't be discussing individually about that. Now we will be moving on to the last part of the video, that is a diagram of all the different series. So let us see. So now we are at the last part of the video, that is atomic spectrum series. Now these are 5 series which are written over here, drawn over here, and we will be learning about each and every series in a brief manner. So first series, we all just learned about it, from any number from n is equals to. So before moving on to that, one difference which you must have noticed is the line size decreases progressively as we go further. So n is equals to 1 and n is equals to 2, the difference is this much big. Then 2 to 3 it is small, from 3 to 4 it is way more small. Why is it like that? Because from n is equals to, what is the energy of n is equals to 1? It is minus 13.6. What is the energy of n is equals to 2? It is minus 3.4. So to reach from 13.6 to 3.4, here you need 10.2 electron volt of energy. While from 3.4 to minus 1.5, what do you need? 3.4 minus 1.5, 0, 1, 10, 9, 4. 1.8. Just 1.8 electron volt of energy is required. So that is why here the difference is 10.2 electron volt, here 1.8. Similarly, it keeps on going smaller and smaller. So from any number, n is equals to 2 to n is equals to 1, n is equals to 3 to n is equals to 1, from n is equals to 4 to n is equals to 1, this series is called as Lyman series. This series falls under UV region. Then comes this series which reaches to n is equals to 2. This series is called Balmer series. This comes under visible region. Then we have from n is equals to x, it comes to n is equals to 3. This thing is called Paschen series. This comes under short IR, short infrared series. Then after that, from anywhere it comes to n is equals to 4. This series is called bracket series. This falls under IR, infrared. And after Lyman, Balmer, Paschen bracket, we have the last one, P-Fund series, which comes under IR. So these are the different atomic spectrum series: Lyman series, Balmer series, Paschen series, bracket series, and P-Fund series. P-Fund is it's not P-Fund, you say that Fund series. So Fund series, where it reaches to n is equals to 5 orbital. Bracket series, when it reaches to n is equals to 4. Paschen series, n is equals to 3. Balmer series, n is equals to 2, and Lyman. So in this series, Lyman, Balmer, Paschen, bracket, and P-Fund series, when you are going from here to here, lambda increases. Wavelength is increasing. Here it was what? 1216, I guess. Then Balmer series started from 6000. So it started from, I'm sure, 4,000 to 8,000, between that only. Paschen series will go more than Balmer series. Bracket series will go more than Paschen series, and Fund series will go more than bracket series. So here lambda increases, wavelength increases. As wavelength increases, energy decreases. That point also, E is inversely proportional to lambda. Here more energy is released, so here less wavelength. Here less energy, wavelength is increasing. Here least energy, it has the highest wavelength. So this was all about the atomic spectrum series. Now one more small topic, that is, if you are exciting an electron to some n is equals to x level, it comes back. How many how many times, how many possibilities are there for it to reach to n is equals to 1? Very short topic, let us see. So now we are going to the last part of this video, that is finding the number of transition. So for example, you excited an electron from orbit number 1 to orbit number 4. Now it has to come back from number 4 to number 1. What are the possible ways by which it can come back? One possible way is that it can directly go from 4 to 1. One way is it will go from 4 to 3, then from 3 to 2, then from 2 to 1. Another possible way is it will go from n is equals to 4 to n is equals to 2, and then from n is equals to 2 to n is equals to 1. So these are the possibilities of the electron to reach n is equals to 1. So what are the possibilities? Possibility number 1 is this. No, or else one more possibility. It will go from here to n is equals to 3, then from n is equals to 3 directly to n is equals to 1. These are the possibilities by which it can reach n is equals to 1. So now if it goes from 4 to 1 directly, it goes to Lyman series. From 4 to 3, then 3 to 1, then it will be 4 to 3 is Paschen series, and then 3 to 1 is Lyman series. So the thing is, what are the possible methods of it to reach the ground state, n is equals to 1. So in this situation, the number of methods are, this is 1, this is another one, 2, this is 3, this is 4, from here to here, this is 5. This thing we will not count, because already we have counted it over here. This thing also we won't count, because this is already counted over here. and this is 6. So there are 6 methods are there for it to reach from n is equals to 4 to n is equals to 3. So n is equals to 4 to n is equals to 1 possible ways are 6. But this is just for a small number, 4 to 1. What if they give from n is equals to 6 to n is equals to 1? We can't always draw the numbers. So for that we have a formula over here, n2 minus n1 into n2 minus n1 plus 1 by 2. So for example, assume the same situation over here. From 4 to 1 we have to go. So here possible ways are 6. From 4 to 1, right? So let n2 be 4. 4 minus 1 into 4 minus 1 plus 1 by 2. 4 minus 1 is 3. 3 into 4 minus 1 plus 1. Sorry. Yeah, so it will be 0. So 3 into 4. 6. So what we did was n2 minus n1. 4 minus 1 is 3. Minus n1 plus 1. Here it is equal to 0. So n2 is 4. So 2 1s are 2 2s are 4 minus 1 is 3. 3 2s are 6. So number of possible methods. Here also it is 6. Here also it is 6. So this is one formula by which we can find the number of possible ways. Similarly, for example, n is equals to 3 to n is equals to 1. So if you are taking 3 to 1, this is one possible way directly. One is like this, one is like this. So possible ways, I think there are 3 only. So n2 minus n1. So that is 3 minus 1. 2 into 3 minus 1 plus 1. 2. Sorry, 3 by 2 is equals to 3. So there are 3 possible ways to return from n is equals to 3 to n is equals to 1. So this was the formula for number of transitions. So I hope you have enjoyed today's video. In today's video we completed atomic spectrum. In the next video of this series we will learn about Planck's quantum theory. So I hope you have enjoyed this video. Like this video if you find this informative. Subscribe to this channel if you are new here. Press the bell icon for updated notifications. See you next time. Thank you and goodbye.